Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we are going to be learning about thermal expansion. We're continuing on in our unit of heat and we're going to be talking today about linear and volumetric thermal expansion. Later on in this lesson we'll be doing some calculations for them, but for now we just want to go over a base definition that you can work with. So we know that when we look at a structure, our materials at the level of the atoms and molecules that make up those materials, thermal expansion can happen. And that's because inside everything, like for example, think about if you're in your roof, you have beams. If you are in an industrial building, those beams might even be made out of metal, right? You might have a metal roofing structure. And what could happen is as the temperature increases, the atoms within that substance, they will get further apart. And we know that that happens, right? As you heat things up, atoms tend to move further away from each other and they move faster, right? So we know that as, think about just, look at this picture here. This is a thermometer with mercury inside of it, right? As we heat up the water around the mercury, some of that heat transfers to the mercury within the water. And it's not like someone's sitting there adding mercury into the thermometer to get it to go up. The only reason the mercury is changing levels within this thermometer is literally because the atoms within the mercury are expanding. When they expand and get further away from one another, they take up more volumetric space, and that causes the level of the mercury to expand. And you can see the same thing happening to the water, right? No one's poured more water into these containers, but as the temperature of the water increases, the water molecules move further away from each other. They start moving faster, right? And you might see that in some boiling action going on. The molecules actually moving fast and boiling. And the volume increases to the point where in this container, the liquid starts to spill out, right? The pressure gets too high and the liquid spills out of the container. Let's take a look at this video. This video's meant for kids, and that's okay. It's gonna be a little bit cheesy, but it does explain visually and verbally quite well some of the properties of thermal expansion. Here we go.
Hey, did you notice that the level of mercury in the thermometer rose when it was placed in hot water? You must be wondering why this happened, right? It happened because of thermal expansion. Thermal expansion is the tendency of matter to expand on heating. This tendency of expansion can be observed in solids, liquids, as well as gases. Now, let us see how this concept of thermal expansion applies to a thermometer. A thermometer usually consists of a narrow tube with a small bulb at its one end. The bulb and a part of the narrow tube is filled with mercury, which is liquid at room temperature. Now, when a thermometer is placed in hot water, mercury inside it expands due to thermal expansion, and as a result, its level rises.
Huh?
You must be thinking how the gasoline came out of the tank, even though it was exactly filled till the brim. Am I right? Gasoline also expands on heating. So, what happened is that when the tank was filled till the brim, there was no space left in it. Now, when the bike was kept in the sun, the tank became hot, which eventually heated the gasoline filled in it. As a result, the gasoline expanded. But since there was no space left in the tank, expansion forced gasoline to come out of the tank.
Hey! Oh, yeah!
Do you think that the rails bent because of thermal expansion? If yes, then you are absolutely correct. A railway track is made up of a number of rails joined to each other. These rails are usually made up of steel. Steel expands on heating and contracts on cooling. When the rails are joined to one another without leaving any space for expansion, the rails bend due to thermal expansion and the train goes off the railway track. To avoid this, the rails are not joined together firmly. Instead, each rail is connected to the other in such a way that a small gap is left in between them. These small gaps provide space for easy expansion of the rails, which happens during summer, as well as due to continuous friction between the train wheels and the rails. Hence, these small gaps prevent the rails from bending, preventing any kind of accidents.
Okay, so I know that was silly, but I think it kind of gets the point across a little bit, right? When we're building things, especially things like, railway tracks, we have to be very careful with that, right? If we don't leave that gap, the rails will bend, and in Canada, we have to deal with winter, right? If we don't account for the contraction, that could be kind of a scary thing as well, right? So we do have to take all of this into account, especially for those of you that are thinking about going into the trades where you'll be building things with metal, or those of you going into engineering. So let's look at first linear expansion. Linear expansion happens with solids for the most part, with thin solids, right? Long and thin objects. I'm just gonna go to the highlighter here. So all solids expand in all directions, right? They're expanding in length, width, and thickness. That's fine. And also they will cool when they're contracted, right? But for long, thin objects, things like beams in your roof or railway tracks, the change is mostly only noticeable when it comes to length, right? If something's long and thin, it's going to get longer. We're not really worried about the change in the width. And when we're discussing the change in the length in that one direction, we call it linear expansion. So that's what we're going to be focusing on for this first part here. And linear expansion is going to depend on three things. What's its initial length? What's the change in temperature we're dealing with? Is it going from 20 degrees Celsius to 60 degrees Celsius? Is it going from 21 degrees Celsius to negative 30 degrees Celsius? What's the change? And then finally, what type of material are we working with? Obviously, different metals have different levels of conductivity, right? They transfer and absorb heat at different rates. That's why we use different types of cookware in our kitchen. What are some types of cookware that you know we use? And what do you have in your kitchen? You probably have some copper pots and pans, maybe some aluminum pots and pans. Some of you might have some kind of alloy that involves a mixture of one of those things with stainless steel, right? We like stainless steel. It looks nice. It doesn't, react with other elements very well. So then you don't get your food, the elements in your food reacting with your pots and pans, the acidity of them, the food, I mean. So, but the thing about stainless steel is it's not a very good conductor of heat, right? So we can't just have a stainless steel pan. That wouldn't actually cook very well. Instead, we make an alloy of it, right? We mix it with other things that do conduct very well. Anybody know how to remove a lid from a sealed jar when it's stuck? I'm sure you've encountered this. You're working with that jar of jam or whatever, and you just can't get it undone. It is stuck as hard as can be. Well, what's the best way to do it? Use your knowledge of thermal expansion. Go to the sink, turn that hot water on as hot as it goes, and place the lid, just the lid of the jar, underneath that hot water. And what's going to happen? The heat from the hot water is going to warm up the lid. The lid is made of metal, conducts heat very well, so it's going to absorb that heat, and the atoms in the lid will actually expand, and the lid will expand, meaning it's no longer so tight and you can open it really easily. Try it. It's a great life hack that has to do with science. Here's our formula. So we have delta L equals alpha L, well, just alpha, not alpha L. Alpha L naught, or the original length, times delta T. So let's go through these terms. Delta L is the change in length, right? We know that. We've been dealing with delta for a long time. Delta means change in. Big L is going to be length, right? So delta L is going to be the change in length. And we're going to use meters. Why? Because that's the standard international unit for length. Alpha is the coefficient of linear expansion. Let's show you where to find these real quick. If you look at Schoology, under our unit of heat, in HT1, the first unit of heat, you will see your coefficient of thermal expansions right here. Now this is going to be a list that's going to be updated, right? If we encounter a problem where we do not have the coefficient of thermal expansion for something, I will just let me know, send me a message, and I will input it onto this sheet by just doing a quick Google search. But I want us all to be using the same coefficients of linear and volumetric expansion so that we have the same answers, right? So that there's a little bit of standardization in our processes of solving for these. All right, so that's where they are. Let's go back to the notebook. L naught, or sometimes, like if you want to replace this O with an I, that's fine. L naught is the original length or the initial length, right? It's what the length started off with. Delta L is the change in length. So this is LF minus LI. And LF is usually called the final length. Li is the initial. Change in length is your LF, your final length, minus your initial length, right? This you could replace. Like if you want it to say Li instead, that's fine. Original, initial, they're kind of the same thing, right? So change in is your final minus your initial. This is just your initial. There you go. And delta T is the change in temperature, right? So final minus initial temperature. So delta T is the final temperature minus the initial temperature. All right. Again, here's the table. You guys have it on Schoology for the practice problems. Let's give a practice problem a shot. So suppose there's a steel beam running across the width of our classroom, and the length is 8 meters. Okay. So we have our initial length is 8.0 meters. And we also know that it's steel. And steel is going to tell us our alpha. Okay. Let's go back to our table. Where is steel? Here. And it's 12. 12 what? 12 times 10 to the negative 6 Celsius to the negative 1. Okay. 12 times 10 to the negative 6 Celsius to the negative 1. Good. We also have this. Due to the bizarre heating controls in our school, the temperature can fluctuate anywhere between 15 Celsius and 30 degrees Celsius. How much would the length of the beam change? Okay, so what's our change in temperature? It's 15 degrees Celsius, right? We can go anywhere from 30 degrees to 15 degrees. What's the difference between them? 15 degrees. Okay. Our change in temperature is 15 degrees. How much would the length of the beam change? So what would be the change in the length? That's what we're being asked. And so I like to start with this. What am I given? What am I trying to find? And then it's as easy as plugging it in, right? We're solving for delta L. We don't know that. Alpha is 12 times 10 to the negative 6 Celsius to the negative 1. And if you don't know what Celsius to the negative 1 means, remember this is negative 1 as an exponent means it's on the bottom. It's on the bottom of a fraction. So this and this are the same thing, right? Celsius to the negative 1 means you drop it down. So this is 12 times 10 to the negative 6 per Celsius, or Celsius to the negative 1. Then we're going to multiply by the initial length, which is 8.0 meters. And then by the change in temperature. What's my change in temperature? 15 degrees Celsius. And now you can probably see why that Celsius to the negative 1, understanding why it's below a fraction, is going to be useful to you. If you have Celsius below the fraction and Celsius above the fraction here, they're going to cancel out, right? So what unit are we going to be left with? Just meters. And let's type this into our calculator. We have 12 times 10 to the negative 6 times 8 times 15. How many sig figs do we want? 2, 2, 2. So our delta L is going to be 1.4 times 10 to the 1, 2, 3. 10 to the negative 3 meters. There we go. So it's not going to change by much, but it will change. For those of you on YouTube, give this a shot, come back when you're done, and pause the video now. For those of you on YouTube, welcome back. We have the solution here for you. So we started off just by writing out our givens. And we know, what's going on here? My computer's acting up today. Whoa. Here's our solution. We started off by looking at our givens. So we were told that it's a steel bridge. We looked up steel from our table, and it was 12 times 10 to the negative 6. The initial length was 380 meters. And our change in temperature, well, it's going from 30 degrees to negative 40. So that's a 70 degree difference in temperature. And we're finding our change in length. So you just plug them into your formula, right? You have delta L equals our coefficient, our length, and our change in temperature. And you plug that into your calculator and you should get something like this. Remember that we only want 2 sig figs here. So we need to round this 1 up because of the 9 before it. So it's actually 0.32. And when you write that in scientific notation, it's 3.2 times 10 to the negative 1 meters. Last thing we're going to be doing here today is volumetric expansion. Remember that linear expansion mostly happens in solids. Volumetric expansion, on the other hand, is going to be happening in liquids and gases. And volumetric expansion is going to depend on three factors, very similarly to linear expansion. We are going to care about the initial volume, the change in temperature, and the type of substance that is undergoing volumetric expansion. Let's get started. The only thing that's kind of different is our formula is a little bit different, right? We've got the change in volume. The change in volume is in meters cubed, right? Length times width times height. So meters times meters times meters. Meters cubed. We have beta now instead of alpha. Beta is the coefficient of volume expansion. And, you know, if we go back to our table, you will see for many of them, well, these ones for the most part, you will have your coefficients of volume expansion. Now, I will be updating the tables as we go. If we need volume expansion coefficients for other problems on Schoology, you will find them, right? I'll update that. You have V naught, or the original volume, and that's also going to be in meters cubed, and then delta T, which is the change in temperature. Let's go ahead and try this problem out. A diesel tank in a truck holds 75 liters at 20 degrees Celsius. So let's start off by writing down our known values. Okay, it's diesel, so I know I'm probably going to have to find the coefficient of expansion, the beta value for diesel. Actually, no, because it's asking us what is the coefficient of volume expansion. So beta, that's what we're trying to find. What is the volume coefficient for diesel? We know that the truck holds 75 liters and the tank is filled to the top. So our initial volume is the tank filled right to the top, which is 75.0 liters. And the daytime temperature increases to 37. So it's going from 20 degrees. Okay, so we want our change in temperature, and it's going from 20 degrees to 37. So our final temperature minus our initial temperature is 17 degree difference in temperature. So our change in temperature is 17 degrees Celsius. And we know that 1.32 liters of gas overflows from the tank. So we can think of it like that example from the video, right? If the gas tank is completely filled to the top, and then this gas spills up, there you go, there's a spill. This amount of gas was 1.32 liters. And so if we went from being completely filled to now we dumped this amount of gas, this is actually the change in fuel. So your change in liters is 1.32 liters. That's how much volume of gas left our tankard. So since we're going to be solving for B, let's go ahead and isolate B first before we plug in our numbers. So we're going to have to get rid of V naught and delta T. And the reason why is so that B is isolated, right? And when you divide something by itself, they cancel out. But you can't do that just to one side, right? So we're going to have to also divide this side by V naught and delta T. And there we go. Now we have delta V over V naught delta T is equal to beta. And we can just start plugging in our numbers at this point. So our delta V, which over here I labeled as our change in liters, I should probably leave it as our change in volume. Okay, there we go. So delta V is 1.32 liters. Our initial volume was 75.0 liters, and our change in temperature was 17 degrees Celsius. And when you do that calculation, you will end up with your final answer. In terms of units, these liters are going to cancel out, and you're just going to be left with Celsius on the bottom. Now let's plug this into our calculator. We have 1.32 divided by whatever 75 times 17 is. And we get that. So beta is going to be equal to 0.001035. We need to convert our answer into the right number of significant figures in scientific notation. Now, normally it's times 10 to the negative 6 Celsius to the negative 1, right? So if I put the decimal place there, that's going to be times 10 to the negative 6. So I could say that beta is 1035 times 10 to the negative 6 Celsius to the negative 1. But I don't have 4 sig figs, right? I only have 2. And so this I would have to round off to, well, this would round down, and so it would be 1,000, right? And now I'm running into an issue where this looks like it only has 1 sig fig, even though it should have 2. So I'm actually going to scrap this idea of using the times 10 to the negative 6, because it's not really going to be convenient for me here. And instead, I'm going to do my normal scientific notation, putting my decimal place there like it normally would, and counting backwards here. So 1, 2, 3. So my answer would be 1.0 times 10 to the negative 3 Celsius to the negative 1. And it might not be in the 10 to the times 10 to the negative 6 format, but that's okay. This is preferable because it has the right number of sig figs, and it's also in scientific notation. So that's preferred. Good. Your turn. Gasoline tank in a truck holds 60 liters at 20 Celsius. The tank's filled to the top at this temperature, so it's similar to the last problem. The daytime temperature increases to 45 degrees Celsius, so from 20 to 45. So you know your change in temperature there. And 1.4 liters of gas overflow. So again, we know our change in liters. What's the coefficient of volume expansion? I'm going to grab the formula for you guys. There you go. Give it a shot, pause the video here, and come back when you have the answer. YouTubers, welcome back. We have the solution for you. Let's go through it. So we know that we have a gasoline tank, and it's in a truck that holds 60 liters, and the tank is filled to the top. So this is our initial volume. The change in temperature, well, we went from 20 to 45, so that's a difference of 25 degrees Celsius. And 1.4 liters of gas spilled out, so that's our change in volume. And we're looking for the volume expansion of gasoline. Well, if we isolate our formula like we did last time and plug in our numbers, we're going to see a few things that are happening here. Liters cancel out, and we end up with this answer. I'm just going to make this a little clearer. This is a 0.933, and you can see the work in the calculator on the right-hand side. Now, we need to talk about significant figures here. Again, this has a maximum amount of 2 sig figs, and it's limited by the significant figures of the temperature, which only had 2, right? We, again, would prefer this to be times 10 to the negative 6 Celsius to the negative 1, because that's how our answers normally are going to be. And if we think of an invisible decimal place there, this would move 1, 2, 3, 4, 5, 6. So that's where we want to put it. So our beta value, our preferred beta value, would have 2 sig figs and have the decimal place there, which would be 930. unlike the previous problem, you have to do a little bit of troubleshooting to figure it out. If you can have times 10 to the negative 6, you really should. All right, that's it for today. Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.